So we have 256 numbers, number from 1 up to 256. What you see is that a whole bunch of these numbers are very small, okay? And a whole bunch of them are quite big, and then there's some transition region that's happening, like some number of channels are mediocre. I have a whole bunch of very good channels. These are the channels which are here to the left, okay? Indices which are there. Those are very good channels, almost zero erasure probability. The ones on the right, they have erasure which are very close to 1. And then there are some channels in between which have still mediocre erasure probabilities. Let me do this a few more times. Okay. Yeah, that's 8 times. Let me do it a bit more. So I can simply take the the 16 polarization steps. I took the things I've already done 8 times. I do it a few more times. Sort these numbers. Hold on a second. Okay. So I have 2 to the 16 channels, 65,536 channels. Okay. You see, a huge majority of them are. About 90% of these channels are very good. About 10% of them are very bad. And then there is some transitionary number of channels which are still mediocre. They haven't become fully rich or fully core yet. So what you see is that you see this phenomenon of polarization. So at the end of this process, you end up with large numbers of very good channels, large numbers of very bad channels, and few neither good nor bad channels. And the fact that we have preserved the average erasure probability tells us that if this curve was exactly a step function there, then it must have had exactly 90% of very good and 10% of very bad channels, because the average erasure probability needs to be exactly 20. But in this whole process, I'm not changing the total. The sum of these p's are not changing. So what we see is that, at least empirically, what we see is that if I keep doing this process, if I keep doing this this transformation, I end up creating these extremal channels. Is it clear what I'm doing, by the way? Is it clear or wrong? Because he's not a computer person.
No, I'm actually really impressed by your. I never had the courage to do this in real time.
That's the worst that can happen. Things don't work like that. So we're back to it. No. Okay. Good. We could go even one more step. I'm not using my laptop is like 8 years old. It's not like this is some fancy machine with fast power and so on and so forth. This is all
sorting is usually the most time.
Yeah, sorting is the most time. That's multiplication. Okay. All right. What I could even do is the following. We could even do this. Let me. We had this do a running sum of these things. So you normally plot the erasure probability, but the accumulated erasure probability until that moment. So you also see the following thing. Not only is are the erasure probabilities of the channel small, if I simply accumulate the sums from the left to the right, they still remain small, and then of course they jump much more quickly because I'm integrating from the left to the right at this moment. I cut off the plot at 1, of course the sum goes to the 0.1 times 65,556, because the sum is preserved. So you see that not only channels are good, in fact they are really good, so that even if you sum the erasure probability starting from the best to the worst, the sums are also very small. Of course, this might be due to the numerical inaccuracies of the computer. You might say, okay, look, maybe you got some underflows at some moment. So should you believe in this plot? It's not so obvious. But we'll see about this thing later on. Okay, so I think at this moment we can go back to this thing. My poor man's screen blank. What we have seen so far is the following. What we have seen so far is so we have this, the mutual information is preserved by this transformation. And secondly, that we also have this property there. Now, so we have this inequality, but we don't really know by how much are these two synthetic channels are unequal to each other. For the erasure case, what we have is the following. For the erasure case, what we have is this. We have IW, which is 1 minus P for the erasure channel. And here let me plot the IW plus minus IW minus. Let me also divide this thing by 2. Since I have the sum divided by 2, let me also plot the difference divided by 2 also. So for the erasure channel, what we have is this is 1 minus P squared is the IW plus, and then 1 minus 2p squared is the minus. So the ones cancel, okay, and then we get 2p squared minus p, or something like that. 2p minus 2p squared. This becomes 2 times 1 minus p. Is the correct? Right. So what we get is a curve like this. So this is the case for the erasure channel. Okay. Now, it turns out that such a thing is true no matter what. Okay? For every channel, for any kind of channel, you end up with whether this is erasure channel or not. Picture such as this, that no matter what W that you have, no matter which channel that you start off with, okay, if you plot on the x-axis the mutual information of the channel IW, on the y-axis this point that you have, you're going to end up at a point which is living in this crescent. Okay. The upper boundary of this crescent is indeed what you get from the binary integer channels. So the BECs trace the upper boundary, okay, and the BSC traces the lower boundary. This is the BEC family is there, and the binary symmetric channel family traces the lower proof here. So this requires proof, okay? At least this one requires proof. I don't need the top one, but I need the fact that that you cannot be living here is important. But this graph is saying the following thing. Unless you're already extreme, unless you are close to the 0 and the 1, this operation here, this polarization operation here, creates inequality. So this is the inequality created. The difference between the plus and the minus channels is exactly this vertical axis there. So they're saying that the only way not to create inequality is to already start from a case in which you're already at the extreme of channels. Everything else creates inequality. That's the meaning of this. Yes.
So it's not only that we require a proof for the BSC curve, but
yes,
every other binary channel,
yes, of course,
it lives in between. It
exactly,
also requires proof.
Yes, the proof I need is the following thing. That the proof I need is that every channel lies above this lower line that I had here, and I claim that's up to the BSC curve. Sorry, I was unclear. You're right to question this. What I was trying to say was that not that the BSC curve traces that particular thing, but that the BSC is indeed the least polarizing of all channels. So now, we do this, okay, so why not? Now let's see. Now first of all, notice the following thing. This, you have these three quantities, IW, IW minus, and IW plus. On the real line, they are exactly in this order. W minus is worse, W is here, W plus is the better. In fact, the average of these two numbers being the same as this, the half the distance between W plus and W is the exact distance between the W and W minus. So this point that I have here is nothing but the IW minus the IW minus. Now let's take a look at the meaning of these quantities here. The IW minus is a mutual information between U1 and Y1, Y2. And U1 is nothing but the x1 plus x2. So this is equal to nothing but the entropy of the x1 plus x2 minus the entropy of x1 plus x2 given 1, 2. This is 1. these x1 and x2 are uniform flips. The 1 minus the entropy of x1 plus x2 divided by 1 given by 1 minus 2. Whereas IW itself is the mutual information with x and y, that is x1 and y1, so forth. It's also equal to the mutual information between x2 and y2 also. So it's equal to 1 minus h of x1 given y1. So now, what we're trying to understand is the following thing. I give you a particular value of the IW. You want to know what can be IW minus p. So that's exactly what we're trying to say. So I specify the value of the entropy of x1 given y1. And we want to know what is the entropy of the x1 plus x2 given y1. So there we have, what do you call this thing? This is Gerber's lemma. Gerber's lemma says the following thing. It says the following. If x1, y1 and x2, y2 are independent, not necessarily independently distributed random pairs, okay? With each of these xi's being binary. And if I